Hi everyone, this is Dr. K. Kavithamani, Associate Professor, Science and Humanities, Hindustan College of Engineering and Technology. Today, I am going to give introduction about residues and Cauchy's residue theorem. So, first of all, understanding the residue theorem. The ultimate goal of the residue theorem is to find the area under a curve. So, suppose you are given a function f of x whose curve is represented in the following figure. The shaded part in figure 1 underneath the curve represent the area that we want to find. In calculus, we use something called the integral, that is denoted by integral f of x into dx, which is to find the area under f of x, but at times it can be too difficult to integrate due to the function and or the limits of the integration. By transforming the function to the complex plane do a couple tricks in order to apply the residue theorem, because that gives us a way to solve the integral by simple calculations. Basically, the residue theorem evaluates integrals by means of a simple calculation instead of having to identify what integration technique to use and how to apply it. So, this is the diagram. So, what I mentioned the above. So, the solution of this diagram is, the first one is real and the second one is complex plane. So, for a conceptual understanding of the residue theorem, it is important to know the difference between the set of real numbers and set of complex numbers, that is R and C. A similarity between the two sets is that there is a one-to-one correspondence between real valued functions and the real part of complex valued function, that is figure 2. Since a complex number is made up of two independent variables, it would be difficult to graph a function of complex variables and find the area under the curve using the technique used in the real plane, where the integration is over an interval. Unlike the real plane, the technique used in the complex plane is integration, that is integration of a function of complex variable along a contour, that is known as contour integrals, line integrals or path integrals. So, now let me explain residue at a simple pole A. That is, residues at a simple pole, residue of f of z at z equal to zk equal to limit z tends to zk into z minus zk into f of z. So, f of z is nothing but given function. Next, let me explain the formula for the residue at a pole of mth order. So, for a given f of z value, how to find out the residue of f of z means, residue of f of z at z equal to z naught equal to 1 by m minus 1 factorial limit z tends to z naught d power m minus 1 by d z power m minus 1 z minus z naught the whole power m into f of z. So, these two are residue at a pole, simple pole and pole of order m. Next, let me explain Cauchy's residue theorem. So, Cauchy's residue theorem is integral over c f of z dz equal to 2 pi I into sum of the residues. That is, we have to find out in each and every point residue of the given f of z. Here S1, S2, S3 etc. are isolated points. So, we have to find out residue of each and every point. Therefore, then finally we have to add all those residue of f of z at all the points. Hence, we have the result integral over c f of z dz equal to 2 pi I into sum of the residues. Next, So using this we are going to see some problems, that is calculate the residue of f of z equal to 1 minus e power 2z by z cube. First let us take f of z equal to 1 minus e power 2z by z cube. Here just let us see the denominator part. The denominator part z equal to 0 is a pole whose order is 3. So we have to use the second formula, that is pole of order m. Residue of f of z at z equal to 0 is 1 by 2 factorial into limit z tends to 0 d square by dz square of z cube into f of z value is 1 minus e power 2z by z cube. Here z cube get cancelled. After that we have to take the differentiation once of the part 1 minus e power 2z. Hence we will get minus 2 into e power 2z. Again we have to take the differentiation. Therefore we will get minus 4 into e power 2z. So 1 by 2 factorial into limit z tends to 0 into minus 4 into e power 2z. So if we apply the limit point z equal to 0, then we will get minus 4 by 2. Therefore the answer is minus 2. Next problem, find the residue of f of z equal to z by z minus 2 the whole square at its poles. So first of all let us take the given function f of z equal to z by z minus 1 the whole square. Here z equal to 1 is a pole whose order is 2. Hence we have to use the second formula again. So residue of f of z at z equal to 1 is 1 by 1 factorial limit z tends to 1 d by dz of z minus 1 the whole square into the given function f of z is z by z minus 1 the whole square. Here z minus 1 the whole square, z minus 1 the whole square get cancelled. Therefore the remaining term is z alone. Therefore limit z tends to 1 d by dz of z is 1. Therefore the value is 1 of the given function, that is this is the residue of f of z at the given point z equal to 1. The next question is the function f of z equal to 1 by z minus 1 the whole square into z minus 3 has a pole of order 2 at z equal to 1. So find the residue. Here the given function is f of z equal to 1 by z minus 1 the whole square z minus 3. Here z equal to 1, z equal to 3 or 2 poles. But the question is we have to find out the pole at only the point z equal to 1 and whose order is 2. Therefore residue of f of z equal to 1 by 1 factorial limit z tends to 1 d by dz of z minus 1 the whole square into f of z. So if we apply f of z, then z minus 1 the whole square, z minus 1 the whole square get cancelled. Therefore limit z tends to 1 d by dz of 1 by z minus 3. If we take in differentiation of 1 by z minus 3 is minus 1 by z minus 3 the whole square. Hence if we apply the limit z tends to 1 of minus 1 by z minus 3 the whole square is minus 1 by 4. So this is the solution. The next question is, suppose for a given condition modulus z equal to 2 and the problem is integral over c 5z minus 2 by z into z minus 1 into dz. So in this example here I have drawn some diagram and we can write integral over c 5z minus 2 by z into z minus 1 into dz can be split as integral over c 2 by z plus 3 by z minus 1 into dz. So if we take LCM then we will get the same function. Therefore we can split the term, that is integral over c 2 by z into dz plus integral over c 3 by z minus 1 into dz. So very well we know that by using Cauchy's residue theorem the integral of f of z into dz equal to 2 pi I into sum of the residue. So we have to find out the residue at the point z equal to 0 and z equal to 1. So first let me check whether z equal to 0 and z equal to 1 lies inside the circle or outside the circle. The given condition is modulus z equal to 2. Therefore, z equal to 0 and z equal to 1, both the points are lies inside the circle. Therefore, we have to find out residue at each point. While getting the value residue of f of z at z equal to 0, we will get the value is 2. If we get the residue at z equal to 1, then we will get the value is 3. Hence, 2 pi I into sum of the residue. Sum of the residue is 2 plus 3. Therefore, 2 pi I into 5. Hence, we have 10 pi I. Therefore, by using Cauchy's residue theorem, integral over C 5z minus 2 divided by z into z minus 1 into dz value is 10 pi I. So, these are the some problems of residues, poles and Cauchy's residue theorem. Thank you.